Hey folks, this video is going to be about the Iron It Out worksheet. I'm going to share my screen with you so that you can see this worksheet in front of me. I've written there in the upper hand corner that this worksheet is going to be very similar to our copper silver nitrate lab. That lab that we're doing in class is copper +1 or +2. We got to figure that out. This worksheet is going to help us figure that out. We already know the charges of silver and nitrate in our copper silver nitrate lab, but it's the copper we got to figure it out. I'm not going to actually do your copper silver nitrate calculations, but what I'm going to do is a very similar situation called iron it out. It's similar to your copper silver nitrate lab, and it's similar to your potential lab quiz coming up in the future. So for iron it out, take really good notes so that you do a great job in your copper silver nitrate lab calculations and your lab quiz coming up. Okay, so let's take a look at this. So for questions 1 and 2, we're examining all the possibilities, just like we started examining possibilities in our copper silver nitrate lab. We're going to examine the possibilities now with iron. You guys know iron that can form a +2 and a +3 ion. It's a transition metal. So therefore, if I had an iron nail introduced into a solution, an aqueous solution of cobalt-2 acetate, 2 possible reactions could occur. So we're going to write out a balanced chemical equation if the iron reacts and forms a +2. So we'll have a balanced chemical equation for that. And we'll also have a balanced chemical equation if the iron forms a +3 ion when it is in solution. So iron for both of these equations starts out without a charge, just a solid. So no charge on that iron nail that's going to be put in a solution of cobalt-2 acetate. So cobalt is a +2 because they give it to us here. Acetate is C2H3O2-. You can look on the back of your periodic table for those, for that polyatomic ion charge. But cobalt, they give us the charge here. So let's write the other reactant. It will be the same for both the Fe+2 possibility and the Fe+3 possibility. So if I do cobalt-2 acetate, I'll need 2 acetates to balance out the cobalt. So I'll have to put that kind of looks like carbon monoxide. Let's make it look more like cobalt. C2H3O2. And both of these are in solution, so we got to put aqueous. Okay, so just like our lab that we did with copper, this is a single replacement reaction. Iron's going to kick out cobalt, iron's going to kick out cobalt. So I'm going to form Fe+2 with acetate, or I'm going to form Fe+3 with acetate. So let's do this one first. If I have an iron +2 ion, that means I'll need 2 acetates to write the correct ionic formula. And that's actually going to be in solution. And I would have solid cobalt. Similar pattern to our lab. And then if I have form an Fe+3, now I'll need 3 of the acetates to balance out that ionic charge. It would be in solution, and I would be forming solid cobalt again. All right, so those are my 2 options, but I'm not done yet. I need to balance these. So why don't you guys pause the video and see if you can balance these equations right now. All right, so when you balance these, the Fe+2, hopefully you got a 1:1:1:1:1 ratio. Very nice ratios to work with. The next one, 2:3 to 2:3. Not as nice, but we can still totally handle this. All right, problem number 2. The coefficients of the reactions give the mole ratios of the substance involved in the reactions. Awesome, that's the definition of mole to mole ratio. Determine the following ratios. Okay, so right now we're just writing mole to mole ratios. And this person in the first reaction is all about Fe+2. The second reaction for me is Fe+3. So moles of cobalt to acetate to moles of cobalt. Well, all of these are 1-to-1 ratios, but let's write this out really nicely. For every 1 mole of cobalt 2 acetate, C2H3O2, I have 1 mole of cobalt. It's a 1-to-1 ratio. So this one is just asking you to go back. I'm going to drop states of matter for right now and compare the mole-to-mole ratios. I've got pretty big handwriting, so I'm going to write this one a little more horizontally. For every 1 mole of cobalt produced in this first reaction, I need 1 mole of iron to react. So I'm going to write these horizontally just so it fits better with my big handwriting. All right, moles of cobalt 2 acetate. For every 1 mole of cobalt 2 acetate, I need to react 1 mole of iron. So this problem is really just getting at, can you read the mole-to-mole ratio throughout balanced chemical equations? And we're going to practice our numbers followed by our units followed by our substances. Really make sure that you practice these, because your lab quiz, we're going to make sure that we're keeping track of substances, we're keeping track of our units and our numbers as well. All right, press pause again. See if you guys can now, with the more complicated 2:3:2 ratio, write the same type of mole ratios, but now instead of using all 1s, you'll be using 2s and 3s. All right, so take a look at what I've got here. For every 3 moles of cobalt 2 acetate, I'm going to produce 3 moles of cobalt, 3:3. Please keep it 3:3. Don't reduce to 1-to-1. For every 3 moles of cobalt produced, I need 2 moles of iron. And if I have 3 moles of cobalt 2 acetate, I need to react that with 2 moles of iron. So all of these ratios came from the 2 possible balanced chemical equations, practicing mole-to-mole ratios. Okay, so that was just examining possibilities that can occur once this iron nail is put into a solution of cobalt 2 acetate. But now this paragraph here is going to give you a lab situation. You're not actually doing this lab, but you've done a similar lab, and we are familiar with these types of single placement reactions. So in lab, to determine which of those 2 reactions occurred, an actual experiment has to be analyzed. Here are the results from a student's experiment. They started with a 21.54 gram iron nail. They put it into a solution that contained 2.98 grams of cobalt 2 acetate dissolved in 50 milliliters of water. Metal into an aqueous solution filled with ions. Just like your reaction, the reaction proceeded overnight. They filtered, they dried. 0.92 grams of cobalt are isolated from the reaction. Cobalt's the metal, so that's how I know it's going to be my solid. And we do not currently have a mass for any of the iron 2 or 3 acetate. We don't know if it's iron 2 or 3 yet, but we're going to figure that out. We also know that the iron nail has a mass at the end of 20.94 grams. So I tried to highlight some important information. So now we're going to calculate not possible mole ratios, but actual mole ratios. So we're going to start that by doing the moles of cobalt produced. So make sure, even though that cobalt is in cobalt acetate, we're focused on the moles of cobalt produced, a yield. And this is going to be experimental moles based on the experiment here. So moles of cobalt produced, I know, let's see, what do I know about cobalt? I know that 0.92 grams of cobalt were produced. I know how to get to moles. That's from last unit. And molar mass off the periodic table, there are 58.93 grams of cobalt for every 1 mole of cobalt. So when I cross multiply by 1, divide by 58.93, stick with my given of 2 sig figs, I am going to get 0.0156 moles of cobalt. You might be thinking, Mrs. Lynch, you just said I'm going to stick with 2 sig figs. Keep your sig figs for a little bit while longer because we're going to actually use this. We're not done yet. And we're going to calculate some experimental mole ratios. So I'm going to hang on to a few more sig figs right now because I'm not done yet. I always round at the end. All right, moles of cobalt-2 acetate consumed. Okay, well, we don't know anything about cobalt-2 acetate except there were 2.98 grams of cobalt-2 acetate dissolved in 50 milliliters of water. We know also how much iron reacted and how much iron was left over. So since iron was left over, there was an iron nail to start this process. And then the iron nail lost mass, but there was still iron nail left over. I'm going to know because I can see the leftover reactant, the iron nail is excess. I'm going to assume that all the cobalt-2 acetate was used up in this reaction. Cobalt-2 acetate is my limiting reactant. So I know in this case that 2.98 grams of cobalt-2 acetate, all of that was used up. I want to know how many moles that was. So I found the molar mass of cobalt-2 acetate to be 176.9 grams. And I'm going to drop using cobalt-2 acetate. It's long and this whole proportion is about cobalt-2 acetate. So I'm just going to keep it in the upper left-hand corner. But I know that's per 1 mole. And when I cross multiply, divide, I'm going to hang on to a few more sig figs, keep more than, I think on this one I kept 3. But when I put this in my calculator, I got 0.0168 moles. But I am going to write next to this, this is cobalt-2 acetate. Okay. So since the cobalt-2 acetate is my limiting reactant, my iron has to be my excess reactant. There is literally iron left over. My nail started, I'm going to make this bigger to kind of visualize this. My iron nail started at 21.54 grams of iron. That was on day 1. On day 2, the iron nail got 1 gram-ish. We'll figure it out. Let's find it precisely. 20.94 grams, which when I put in my calculator, oh, not even 1 gram. Sorry, 2 sig figs minus 2 sig figs. This I'll keep the same. 0.60, 2 sig fig, or 2 decimals minus 2 decimals. Sorry, gives me 2 decimals. Only 0.60 grams of iron was used up. I had a larger iron nail, not to scale, and I had a smaller iron nail the next day. That is 0.60 grams of iron. That was the iron used in the reaction. So not all the iron nail, we don't know if it was going to turn into iron plus 2 or 3, but not all the iron was used up. It was left over at the end. So only a portion of the iron nail was going to turn into the iron ions in solution. So I know the grams of my excess reactant. I can now go to moles. So I got to do one more step for this particular part. 0.60 grams of iron. I want to know how many moles of iron that is. And I know off the periodic table, 55.85 grams of iron is in 1 mole of iron. When I cross multiply and divide, I end up with 0.00107 moles of iron. Okay, we've done a lot of work so far. You guys are doing great. So now we know the moles of cobalt that were produced, the moles of cobalt-2 acetate that were reacted, and the moles of iron reacted. We had to be careful with this one, had an extra step because iron was the excess reactant. Now we're going to do some experimental based on this experiment mole to mole ratios. So I'm going to use this experimental data, not what we did up above. That's just a possibility. We're going to compare the experimental to the actual possibilities of mole to mole ratios. That's what's up next. Okay, moles of cobalt-2 acetate. All right, I labeled that so nicely. It's right here. You want to keep track of all your numbers, units, substances again, because you're going to use them here. You're going to use these numbers on the next page. So keep track for yourself. All right, so I know I have 0.0168 moles of cobalt-2 acetate. I know it's lots of writing. You guys can do it. And I'm going to divide that by the experimental moles of cobalt produced. This is 0.0156 moles of cobalt. And when you put this number in your calculator, you end up with 1.07 moles of cobalt-2 acetate, C2H3O2, for every, remember, we're not canceling out units, so it's going to be for every 1 mole of cobalt. This is a 1-to-1 ratio. Okay, well, moles of cobalt-2 acetate to moles of cobalt, 3 to 3, and this one's a 1-to-1. 3 to 3 reduces to 1-to-1. Oh, not enough information yet. I don't know if this is iron plus 2 or iron plus 3. Let's do moles of cobalt to moles of iron. Experimental data. Let's do moles of cobalt. We need that again. 0.0156 moles of cobalt. For every experimental data, 0.0107 moles of iron experimental data. Divide those two in your calculator, and what we end up with is 1.45 moles of cobalt for every, units don't cancel, so 1 is the denominator, 1 mole of iron. Oh, this is not a 1-to-1 ratio, but it's also not a 3 to 2, or is it? If I multiply each of these by 2, 1.45 is very close to 3. 1.5 times 2 is 3. And if I multiply this by 2, I'm going to get 2. Or for every 3 moles of cobalt, I am going to need to react 2 moles of iron, 3 to 2 ratio. Ooh, I'm starting to have proof that it's iron plus 3, because I'm comparing, just like you guys did with Minimol, experimental data to actual data, actual mole to mole ratios. Is it perfect? No, but labs are never perfect, and that's okay. All right, let's confirm that we know that this is iron plus 3 with the moles of cobalt-2 acetate, 0.0168 moles of cobalt-2 acetate. I'll do this one vertically, 0.0107 moles of iron. When I divide this, I end up with 1.57 moles of cobalt-2 acetate. 2, we divide out 1 mole of iron, which again, if we multiply through top and bottom by 2, I end up with close to 3 moles of my cobalt-2 acetate. And I end up with, oh, this one will be perfect, 2 moles of iron. And let's even add this in here, C2H3O2. 2. So yes, indeed, 3 moles of cobalt-2 acetate to 2 moles of iron, experimental compared to actual. This is going to be Fe plus 3. Now, did I have to do all 3 mole ratios? No. Enough is going to be proof with 1 of my mole to mole ratios. But this practice will show you that you can compare any experimental mole to mole ratio to actual mole to mole ratios found from a balanced chemical equation, and you can determine the charge. All right. I'm going to do some of the next page as well. but I'm going to do that in the next video. See you guys then.